Okay, in this presentation we are going to look at an introduction to R for actuarial students. This presentation features probability distributions, in particular the binomial distribution. So the presentation overall corresponds to the CS1B curriculum. That comprises an introduction to R programming, fundamentals of statistical analysis, and probability distributions, which is what we're doing here. This is question 1 of the playlist, the binomial probability distribution. Okay. Now, the playlist and the entire CS1B curriculum is based mostly on the basis of base R. So not tidyverse, not ggplot or anything like that. So we'll focus on base R. The curriculum does advise you to use some packages like for statistical analysis on an ongoing basis, but unless they're mentioned we won't use them. We'll stick with base R. Okay, so this question is the probability that India will win a cricket match against South Africa is 0.7. Prepare a probability distribution table of the number of wins if Indians are going to play 10 matches against the South Africans. Plot a bar chart of the probabilities of the number of wins from 0 to 10 and find the mean and the median number of wins for India against South Africa. Okay, so this is a 10 independent trials, so they're going to play 10 matches, okay, and the probability of winning according to this is 0.7. Okay, so that's a binomial distribution with n, the number of independent trials, is 10. That's maybe a bit hypothetical in sport, but anyway, we'll go with it. And the probability of success, which is an Indian win, is 0.7. Okay, so we're going to set p equal to 0.7. Okay, now the first thing we're going to do is create a table. And we're going to have 2 columns on this table. The first column is the probability. And there is going to be a probability corresponding to each and every single possible outcome and that means out of the 10 games, how many does India win? It can win as few as 0 games, that the South Africans win all 10, or India can win 10 games, okay? And every possible value in between. So what I have here, if you just type that line of that particular segment of code in, what that does is returns a series of integers, a sequence of integers between 0 and 10. Okay, and a sequence of integers can be supplied as an argument to a command like this: dbinom. This is a probability mass function. Okay. D sort of usually means density, but in the context of binomial distribution, it is probability mass function because the binomial distribution is a discrete random variable. Okay, discrete distribution. So dbinom. Okay, that's our inputs 0 to 10. The arguments are as follows: the size equals 10. That's the number of independent trials, and the probability of success is 0.7. Okay, so what I have highlighted there is going to stay consistent the whole way through. So when we calculate that, we get a set of probability values. We get 11 probabilities, okay? 0 included, so 0 to 10 is 11 discrete possible outcomes. Okay, so what we're going to do now is combine that into a single data frame where we have the number of successes, 0 to 10, and the probability of that success. And we're going to save this as a data frame called probability densities. So that's probability densities there. Okay. Now disregard this column here. That's just the sort of a row index. So we won't pay any attention to that. So the number of successes, 0, 1, all the way down to 10. Okay. And beside that is the probability of that number of successes. You can sort of see here that the probability of 6 successes is 0.2001. The probability of 7 successes is 2.668. And the probability of 8 successes is 2.33. And they taper down on either side. For example, 9 is 12% essentially, and the probability of 10 is 2.8%. And on the other side, they're very small probabilities as well. Okay, that's what we're asked to do. Okay. So exercise 2, a bar chart of the probabilities of the numbers of wins. Okay. So what we're going to do is go back to our set of probability values. Okay. And bar chart of the probability of successes. XLab is the number of successes, that's the X label, and the names argument is 0 to 10. Okay. Now, so this essentially is the same sort of information corresponding to the data frame we've just created, but we're setting it up differently. This is a consequence of using base R. So bar plot is the generic command. The probabilities of interest are, we're going to see them shortly. These are some commands just to actually annotate the plot, and this just tells us what each probability corresponds to. Okay, names argument essentially. So there we have it there. Okay, and so essentially that's a visual complement of the graph that we've just created there previously. Okay, so it's a nice pretty graph, to be honest with you. Yeah. Okay. Now, the mean and the median number of wins for India against South Africa. So by definition, which the definition of a binomial mean is n times p, okay, 10 times 0.7, and we get 7, okay. Or we can use the definition of the expectation of a discrete random variable. So what we can do is take out x and let x be the probability densities for the number of successes from that column and the corresponding probabilities. Okay, so we get a multiplication of each possible outcome times the probability of that, and we sum them up. Okay, and then that is our mean, and our mean turns out to be 7. Okay, so this approach is probably a bit more satisfactory on an ongoing basis because this approach can be used in many different scenarios. You don't have to remember what the definition of the mean is from first principles, as in the case here, n times p. In the case of the binomial distribution, it's straightforward enough because you could just sort of come to it intuitively. But if we're dealing with other probability distributions, using the definition of the expectation of discrete random variables, the sum of x times the probability of x, that's a sort of very resilient approach. The median, we're going to use another one of the binomial family of functions. Here it's Q binom, okay. Q is quantile, and this corresponds to what the value here. This is 0.5 as in 50th percentile. 0.5 is this 50th percentile, which is the median. Those are the arguments there. Size equals 10, probability equals 7, and we just calculate the median, and there we go, 7. Okay, that's it. Now, actually, to be honest with you, I'm doing something very naughty there. I shouldn't really call this median because that's a really reserved word. So I should say my median or something like that, or sample underscore median. But anyway, we'll just go with it. Okay, bye-bye.